Hello everyone, thanks for inviting me to present my paper in EastCast 2022. I'm Issa Salame and I'm going to present superconductive logic using 2-phi Josephson junction with half-flux quantum pulses. Computing applications that has been on high demand lately is cloud computing. Many calculations and applications don't run on a mobile device, but instead on a faraway server in a data center which completes the operation and sends us the end results. Data centers consume terawatts of power and a large portion of the world's electricity. Such high power consumption can have environmental impact and high cost. A main candidate for energy-efficient, high-performance technology for the applications specified earlier is superconductive RCFQ technology. RCFQ logic family shows 4 orders of magnitudes improvement in the power delay product compared to conventional CMOS technology. The focus of this talk is to present and show you superconductive circuits, one main disadvantage in this technology and how it can be solved. So I'm going to start with a short background on superconductive circuits, then I'll explain about logic circuits that can be implemented using 2-phi JJ. Then after that, I'll demonstrate our results and conclude our work. Superconductivity. Superconductivity is a phenomenon in which below a certain temperature, the conductor has a zero DC resistance, as you can see in the figure here. With this comes new phenomena such as flux quantization. In a superconductive loop, the magnetic flux must equal an integer number of flux quantum. So each superconducting loop can have 1 flux quantum, 2 flux quantum, 3 flux quantum, and so on. It also introduces new physics which can be used to explore new devices and electronics. The Josephson junction is the active device used in superconductive circuits. It's a multi-layer device built from a superconducting layer, an insulating layer, and another superconducting layer. The figure shows the device layers over here and the device schematic over here. The current in the device is dependent on the phase difference between the superconductive layers, and we can see from the equations below that a change in phase in time can actually cause a voltage on the junction itself. From the equations shown in the previous slide, the energy of the junction can be extracted. It can be seen that the junction prefers to be at 2 pi n phase difference when n is an integer, which means that the junction prefers to be at 0, 2 pi, 4 pi, 6 pi, and so on. Each 2 pi switch of the junction produces a single flux quantum pulse, an SFQ pulse, meaning if the phase of the junction changes by 2 pi, let's say from 0 to 2 pi, then the junction produces an SFQ pulse. The junction is modeled by an RCSJ model, resistively capacitive shunted junction model. The model assumes the junction has a capacitive current, resistive current, and superconductive current. The capacitive current is caused because of the two metal plates and the insulator between them, so it's like a capacitor. The resistive current is caused for relatively high currents that can break superconductivity for the junction, and the superconductive current. Adding those three currents together gives us the total current flowing in the junction, according to KCl. Solving the RCSJ equations with a bias current gives us the dynamic behavior of the junction. If the current is below critical current, which we call IC, then no voltage will be developed on the junction. If the current exceeds the critical current, then SFQ pulses will be produced by the junction. Each SFQ voltage pulse, the junction phase switches by 2 pi as we saw earlier. In this example, the IC of the junction is 100 microamps. Using the Josephson junction, RCFQ logic family is born. RCFQ is the common used logic family in superconductivity. It does not work like semiconductor logic, with VDD or ground voltages. It's a pulse-based logic family. Existence of a pulse is a logic 1, absence of the pulse is a logic 0. The pulses are quantized and equal to a single flux quantum, an SFQ. Because this logic family is pulse-based, each logic gate has an additional clock input. After receiving its logical inputs, the logic gate releases the output when receiving its clock input, depending of course on the logic function itself. This is a simple RCFQ example D flip-flop circuit. When receiving a clock SFQ pulse without a preceding input, the JJ clock will switch, meaning an output pulse will not be produced. When input SFQ pulse enters the D flip-flop, it switches JJ1, and now the loop stores the single flux quantum. The loop has actually a magnetic flux, and it stores it by a circulating current. So because of this circulating current, now JJ2, the bias current in JJ2 is larger. So now when receiving a clock SFQ pulse from the clock input, JJ2 will switch because it has a larger bias current. And when JJ2 switches, it produces an SFQ pulse to the output. RSFQ depends heavily on superconductive loops. It depends on superconductive loops, so it could store the SFQ in them. Each loop has to have a minimum area, so it could store the SFQ, because the flux is equal to the magnetic fields times the area. If we don't want to have a large magnetic field, we need to have a minimum area, so it could limit the magnetic field. And if each loop has to have a minimum area, then we have a scaling problem, because we can't make our circuits smaller. So our contribution, the use of 2πJJ in superconductive circuits actually eliminates the need for inductors, meaning it eliminates the need for large loops to store the SFQ. And the proposed logic gates has an HFQ inputs and outputs. So using these HFQ inputs and outputs, we can actually improve the latency and energy consumption compared to conventional RSFQ circuits. So now I'm going to give a brief background on 2πJJs and show you the proposed 2πJJ logic circuits. 2πJJ. We can build the Josephson junction with a spin-active ferromagnetic layer instead of the insulating layer and have a device with different properties. Different properties like a dominant second harmonic. We saw in the previous slides that a regular Josephson junction has a sinusoidal current phase relation. Now we still have a sinusoidal current phase relation, but we have a dominant second harmonic. We have two harmonics. Extracting the energy phase relation of the 2πJJ shows that the junction can be at pi-n phase differences, meaning at 0, pi, 2π, 3π, and so on, and not only at 2πn phase differences. And each pi switch now is an HFQ pulse, half flux quantum pulse. And from the energy equation, we can see that each HFQ pulse even demands less energy than an SFQ pulse. So we now replace each JJ with the 2πJJ as the switching elements in the proposed 2πJJ logic circuits, and we replace each inductor with the JJ as an impedance, and the stored data in the loops is represented as phase. The pi is a logical 1, the 0 is a logical 0, and we have HFQ inputs and outputs, and not SFQ, and not single flux quantum pulses. The first circuit I'm going to demonstrate is a JTL, a Josephson transmission line. The JTL connects different logic gates together and acts as an interconnect. It passes the HFQ pulse from its input to the output. So, when we have an HFQ pulse at the input, notice that it switches JJ1, then the pulse propagates and switches JJ2, then propagates and switches JJ3, and so on. And notice that only the 2πJJ switches, and the regular JJs just behave as an impedance to redirect the bias current as needed. The next circuit I'm going to demonstrate is an inverter. In the case of receiving HFQ pulse from the clock input, without a preceding HFQ pulse from the logical input, JJ out switches. And JJ out switches instead of JJ clock or JJ in because it has a larger bias current. JJ out has a larger bias current because the bias current IB is divided between JJ in and JJ clock, and eventually, in the end, it is added in JJ out. And this switch of JJ out creates an HFQ pulse at the output. On the other hand, if an HFQ pulse is received at the input, it switches JJ in. Switching JJ in creates a circulating current to create a phase of 2π in the loop. Because as we said before, a superconductive loop has to have a 2πn phase difference. Now the current in JJ clock is larger than before, so when receiving an HFQ pulse at the clock input, it switches JJ clock. Now the loop has a phase of pi from JJN and from JJ clock, so no circulating current is needed, and the circulating current vanishes. So as we saw, when receiving a logical 0 input, logical 1 output was produced, and when receiving a logical 1 input, logical 0 output was produced, as expected from an inverter. For simulations, we revised widely researched Verilog A code for the regular JJ to behave as a 2-phi JJ, and the model was inserted to Cadence Virtuoso and simulated using Cadence Virtuoso. We can see from the inverter voltage simulations that without a preceding voltage pulse to the clock input at the regular logical input, an output pulse is produced, as expected from an inverter. And with a preceding HFQ pulse at the input, the gate does not produce any HFQ pulse at the output. And from the phase simulations, we can see that the 2-phi JJs actually switch by pi, and this switch will actually show to be more energy efficient in the results later on. Lastly, I'm going to demonstrate the OR gate. Receiving an HFQ pulse from the clock input will switch JJ clock, and the pulse will not propagate to the loops or to the output. So if we didn't have any HFQ pulse from the input 1 or input 2, it will result in a logical 0 output. No pulse will be produced at the output. Receiving HFQ pulse from input 1 will actually switch JJ in 1 and produce a circulating current in the first superconducting loop. So receiving an HFQ pulse from the clock input now will switch JJ in 1 back, and this switch will produce a pulse towards the output and switch JJ out, which will produce an HFQ pulse to the output. So a logical 1 from input 1 will produce a logical 1 in the output. And the case with input receiving HFQ pulse at input 2 is very symmetric. It will switch JJ in 2, and then a clock pulse will switch JJ in 2 back, and this switch will produce an HFQ pulse at the output. In the case where we have HFQ pulse from input 1 and input 2, the two superconductive loops have a circulating current, and the HFQ pulse from the clock input now will reset them and produce a pulse towards the output that will switch JJ out, that will produce an HFQ pulse at the output. As expected from an OR gate, we can see from the voltage simulation that each time we don't have any HFQ pulse at input 1 and input 2, we don't have any HFQ pulses at the output, and each time we have pulses at input 1 or input 2, when we receive a clock input, we do have an HFQ pulse at the output. And from the phase simulation, we can see that all the 2-phi JJs switch by pi. So now we go to the evaluation phase. For the results, the latency was calculated as the difference between the output pulse and the arrival of the clock input pulse. When the logic gate doesn't produce an output pulse, we say the latency is undefined, and the energy was calculated as the integral of power consumed over one clock cycle during an operation of every logical input combination. We can see in the results that the RSFQ JTL is 1.7 times slower than the 2-phi JJ JTL and consumes 2.1 times more energy. And comparing the RSFQ inverter with the 2-phi JJ inverter, we can see that the RSFQ inverter latency is 2.2 times slower and consumes at least 2.6 times more energy. And comparing the OR gates, we can see that the RSFQ OR gate is more than 2.8 times slower than the 2-phi JJ OR gate and consumes at least 5 times more energy. So, to conclude our work, we saw that 2-phi JJ logic eliminates the need for inductors, which could enhance scalability, and 2-phi JJ logic enables us to have HFQ data transmission and storage. That the simulation shows us we can have 2.2 times speed up and 2.6 times less energy compared to regular RSFQ. Thank you for listening. I will be more than happy to discuss this further. Here's my email, and you are welcome to send me an email and ask or discuss with me on this topic.